So today we're going to talk about superconductivity, and we're going to do some problems with power and see where that takes us. So superconductivity is the resistance of a material, and the resistance drops to zero. There are certain materials that have no resistance. And this is really important because there's no loss of current over a wire. If you have very, very long wires like in our house, or think about power lines, we're losing current. Now, where is it going? We're losing it to resistance, and it becomes heat and goes out in the atmosphere. That's a total waste. It's a waste of energy, waste of resources. If you're concerned about going green and reducing greenhouse gases, certainly we're losing energy there. A problem, and you're going to see why this is becoming less of a problem, was that you generally had to get close to absolute zero. You generally had to get down to like liquid nitrogen temperatures and really, really cold temperatures to have superconductivity. However, and this should be 2019, excuse me, I have to change that. As of 2019, there was a group in Germany able to make a superconductor at 250 Kelvin. Now, we don't generally think in Kelvin everyday temperatures, but that's only negative 9.4 degrees Fahrenheit. That's actually not all that cold. I mean, we can get to, negative 10. We don't usually get it in the winter around here, but it's absolutely possible. It's not unreasonable. So we're getting closer and closer to making materials that could be used as superconductors, and you have no loss of the energy. However, the problem is these materials are often, they're kind of like ceramics, where they're a little bit brittle. So to make a wire out of them isn't super practical at this point. Most of our wires are things like copper or aluminum, where they're very, very flexible. Now, whether we could alloy it with copper or a more flexible material, I'm not sure. But that's where we are right now, really, really close to room temperature. And in fact, it's, I've heard about this for decades. It's taken decades and decades to get to that point. Now, who uses it? Believe it or not, they're used in MRIs, in hospitals. So to have an MRI, they have to have liquid nitrogen there and particle accelerators, and who knows what applications we'll see. Now, electricity and magnetism are very, very linked. I'm hoping we'll get a chance to talk about magnetism in this course. So what we're seeing is this is the superconductor, and they have it in liquid nitrogen. So the electrons have no resistance. They can run all they want, and they create this very strong magnetic field. And you can see that they're levitating that neodymium magnet above it. And this thing here is in a ceramic cup. It's basically just like a fancy coffee cup would be. Nothing that special to hold the liquid nitrogen. Now, the main body of what we want to talk about today is electric power. And power is measured in watts. A watt is a joule per second. So power, if you remember, it was work over time back in Physics 1. And it still is, because joule is a unit of work or a unit of energy, and time is, of course, second. Now, there's different variations of this formula. We're going to just work with P equals I squared R. And here's the way to remember it. Twinkle, twinkle, little star, power equals I squared R. And it's silly, and you'll hear me say it 2 or 3 times today, but that's okay. Now, there's other variations, but we'll just derive those as we need them. I don't think we need to memorize those other formulas. Again, twinkle, twinkle, little star, power equals I squared R. You can memorize those if you want. Certainly nothing. I'm never going to stop you from doing that. But we won't need them. I'll show you. We'll derive them from Ohm's law. So when we buy any kind of bulb, we're going to buy usually watts. So how many watts is the bulb? This happens to be a 40-watt headlamp. I don't know if that would be for a car, or maybe some bicycles have lights on them. We're going to hook it up to a 12-volt battery. We want the resistance. So power equals I squared R. And what do we know? We know the power is 40 watts. We know the voltage. But we don't know the resistance. So we need a way to get that. So let's see what we're going to do. We don't really care about the current. So V equals IR. So I equals V over R. And I squared would be V squared over R squared. The reason I did that was I want to substitute for I squared. And don't forget you have to still multiply by the R. I just substituted that in for I squared. And of course, one of the R's will cancel. I get this other formula. You can memorize it if you want. All right, so now I'm in good shape. 12 squared is R, over the power, which we know is 40. Alternately, and probably better, I should have said, okay, R is V squared over P. I should have just solved that out. But you could do it either way you like. So 12 squared over 40. So let's see. 12 squared is 144. 144 divided by 40. So think about 14 divided by 4 would be a little bit more than 3. And I'm not even going to bother to double check it on the calculator because I know it's going to be that 3.6 ohms. Now let's see. We have an electric heater drawing 15 amps on a 120 volt line. How much power does it use? We have a couple options here. We know the current. We know the voltage. We don't even have to substitute in there. We could just say, well, all right, these are the pieces I know. Now let's see what I can solve for. I could solve this for R without any heartache. I can just substitute, okay, 120 volts, and that's home power. That's not unusual. 15 amps is really strong, but that's, again, it's an electric heater. It's going to take a lot of power. So that's 8 ohms. Now the power on that, excuse me, I wrote an R. I should have wrote a P. Not going to bother to erase. Twinkle, twinkle, little star, power equals I squared R. Now I have everything I need. 15 amps squared times the resistance of 8. And again, something like an electric heater is going to use a lot of power. And this is 1800 watts. So, I have it on here in slide 2. You can see, yeah, 1800 watts or 1.8 kilowatts. Now, one last problem, and we'll call it a day. This is more of a review problem. A lightning bolt transfers 20 coulombs at a potential difference, that's the voltage, over 20 seconds. So what's the current? So I is delta Q over delta T, which is 20 coulombs over 0.2 seconds. That's going to give us quite a high current. Well, it's a lightning bolt. We'd expect that. 100 amps. Now to get the power, well, let's see what we'll do there. Power equals I squared R. And what do we know? We know the I and we know the V. So V equals IR. I can just divide both sides by I. So I get V over I. And when I substitute for that, see what I did? I knew what the R was, so I just put it in here. I get I squared times R, which was V over I. Now one of the I's will cancel, and I get PIV. Power equals current times the voltage. Multiply those two together, 100 amps, because we found that in the first part, times the voltage, that's 50 million volts, and we get about 5 billion watts of power.